This is my Raspberry Pi custom cooling project. So in a previous project that I worked on, my team and I had used a Raspberry Pi 5 to run a YOLO V8 machine learning model for human tracking. And because of a high CPU and memory load, it caused severe thermal throttling and system instability. While the active cooler that you can buy online fixed the issue, I started this project as a way for me to revisit the issue and utilize some of the heat transfer knowledge I recently gained from my mechanical engineering curriculum. As a disclaimer, I want to acknowledge that this project isn't about being more cost-effective or efficient than consumer products that are readily available. It's about applying my skills with engineering design, fabrication, and thermal analysis. This video will be a brief overview of the project, and there will be a more detailed design report in the description if you'd like to learn more about the design and analysis behind this project. Looking at material selection, I chose C110 copper as the heat-seek material, and I chose it because of its superior thermal conductivity compared to aluminum. For the mounting bracket, I chose PETG, and while materials like ASA or ABS have a higher glass transition temperature, PETG was safer for my current printer setup while offering better strength and heat resistance than standard PLA. And because PETG has a glass transition temperature that is close to peak CPU temperatures, I applied very small layers of Kapton tape, which does a good job insulating at the contact points to minimize conductive heat transfer into the bracket. I also printed this bracket with 5 wall loops to ensure the structure could handle the constant load without creep becoming a major issue. When designing the system, I wanted to avoid covering up as little I/O as possible, like the GPIO headers. Unfortunately, I did have to cover up the CSI cables, however, they're typically flexible. I also wanted to maximize the air volume going over the heatsink, so I created this duct which allows the circular profile of the fan to transition to a square profile of the heatsink. A major design hurdle was that the CPU on the Pi 5 is not centered between the reference mounting holes. So if I applied equal force on these compression springs, the heatsink would tilt, leading to poor contact. So to solve this, I performed a moment balance analysis around the CPU center. The top holes are offset by 20 millimeters, while the bottom holes are offset by 10 millimeters. So with these calculations, the bottom springs need to provide at least twice the amount of force as the top ones. I used 3 of 4 stainless steel springs with a calculated constant of 1.2 newtons per millimeter. With that number, I determined the exact compression needed, 1.39 millimeters for the top compression springs and 2.78 millimeters for the bottom compression springs. Before I left school for winter break, I quickly machined the 20 millimeter square copper slug from C110 copper stock on the Bridgeport mill. For the interfacing material, I chose Arctic MX4 thermal paste over thermal pads, as thermal paste offers significantly lower contact resistance and it fills in the microscopic air gaps, while traditional thermal pads add thickness that increase thermal resistance. So I tested 3 configurations of the Raspberry Pi, one being the active cooler, the other being just the copper slug, and the last one being the copper slug with these prefabricated aluminum heat sinks that I purchased. And I used Raspberry Pi's built-in stress test called StressNG to max out the CPU. To keep variables consistent, I also overrode the Pi's fan control to run at a constant 100%, which allowed me to determine the steady state temperature for all the configurations. Now, looking at the results, they make sense. The stock active cooler leveled off at around 60 degrees Celsius, while the pure copper slug reached around 68 degrees Celsius. When I added the 16 fins, the temperature dropped to 62.5 degrees Celsius. And this highlights a classic trade-off. While the copper has higher thermal conductivity, the active cooler wins because of its 54 fins, which is crucial for heat dissipation through surface area. Using ANSYS, I verified the structural integrity of the PETG bracket and ensured that the deflection of the mounting bracket and bending of the PCB didn't exceed far past 0.1 millimeters. I enjoyed working on this project and applying a lot of the things that I've learned from my courses and previous projects. Feel free to take a look at the design report I put in the description, as it goes a lot more in depth about my project and the analysis behind it, like the thermal resistance circuit and some other design considerations. Thanks for watching.